Okay, so this is problem number 51 in the 7th edition. We just read it, but unfortunately I forgot to turn the camera on, so here we go again. We've got a steam turbine, basically. The steam turbine has steam coming into it at what I will call state 1. It has a pressure of 10 megapascals and a temperature of 500 degrees Celsius. The steam produces power out of the turbine, produces work in the amount of 5,000 kilowatts, in other words 5 megawatts. It's pretty small for a steam turbine. But the steam then leaves at a pressure of 10 kilopascals and a quality of 90%, so 0.9. We're supposed to find out the mass flow rate through the turbine. Let's see if we can do that. The energy balance comes out like as is shown on the screen. Use the one for a turbine that says power output equals mass flow rate times enthalpy change. So power output equals mass flow rate times the enthalpy change across the turbine, which is H1 less H2. And so the mass flow rate could be calculated by rearranging the equation like this. All we need is the enthalpy at the inlet and the enthalpy at the exit. It's easy to look up the enthalpy at the inlet. This is superheated steam. So you just go to the steam tables and you look it up. We're not going to use a CP delta T here because there's a little bit of phase change, and why bother? We can just go look up the number. All right, so why use an approximation? Yes, sir.
What is the problem on this one?
Oh, sorry. This is problem 5-51. So I'll take my system to be all the stuff inside of the turbine. Okay, state 2 is the exit here. And so if you look up the enthalpy, in the interest of time, I'm just going to write it down. It's 3,375.1 kilojoules per kilogram. You can go look that up later if you want to verify it. And for the exit, the enthalpy at the exit, since we have a saturated mixture, is the enthalpy of saturated liquid at P2 plus the quality at the exit multiplied by HFG at P2. Okay? Now this is just using the quality equation. We've done it several times. Complete your notes. It's 191.81 kilojoules per kilogram plus 90% of 2,392.1 kilojoules per kilogram. Okay. That comes out to 2,344.7 kilojoules per kilogram. So when I plug in the number, or the numbers, 5,000 kilowatts divided by 3375.1 less 2344.7 kilojoules per kilogram. Notice what happens. Kilowatts is the same thing as kilojoules per second. So the kilojoules go away, I get kilograms per second, and the amount of about 4.852 kilograms per second. That's the mass flow rate through this thing. The key difference between this and the last problem, not only is the energy balance a little bit different, so we have a work interaction and no kinetic energy changes, but the other difference is that we get our properties, our equation of state information from tables rather than from an approximation of CP delta T. Okay. I always prefer to use tables if I can, because then all I have to do is look something up. Okay. Still have about 5 minutes before 30 till 8. So let me work another problem for you quickly. Any questions on this one?
How did you get HF at P2?
HF, just look up 10 kilopascals. You can get HF and HFG.
Okay.
And read them all.
So 10 kilopascals from the expression tables for superheated.
Right, now how did I know to look it up? Because I knew that I had some liquid and some vapor in the excess or saturated.
That's why you had to use HF at P2 and quality times HFG.
That's right, because I needed the average and it would be at the exit.
Okay.
Yep. Good questions. Anything else? All right. Well, this is problem number 68. I'll read it to you quickly. Refrigerant R134A at 800 kilopascals, 25 degrees Celsius, is throttled to a temperature of -20 degrees. Determine the pressure and internal energy of the refrigerant at the final state. All right, let's find out. And by the way, if I erase this and you haven't got it all written down, you can grab all of this via PDF and the examples on Blackboard. So you really don't have to write any of this down if you don't want to. So this is 5-68. All right, so here's the system. Got a throttling valve. I'll drop this way this time. Thought as if it would have a handle on it. Most of them don't. But they do have a control of some type if they are an adjustable valve. Quite a few air conditioning valves today are. TVXs are valves that are thermally adjusted basically. Based on temperature. Then we have an incoming stream of R134A that has a pressure of 800 kPa and a temperature of 25 degrees Celsius. The temperature at the exit is -20 degrees Celsius. Now the solution to this, the energy balance, is pretty trivial. Remember I showed you the energy balance for throttling valve? It just says enthalpy in equals enthalpy out. So the enthalpy at state 2 equals the enthalpy at state 1. This is the result of the energy balance. It doesn't seem all that beneficial to us. Now Cp delta T doesn't make any sense here, right? Because there is no delta T. But there is a change, there's no change in enthalpy, but there is a change in phase, and so there could be a change in temperature. Okay. All right. Now, if you look up, in fact, if you would, open your books to the R134A charts and look up a pressure of 800 kilopascals. Or better yet, look up a temperature of 25 degrees Celsius. Go to the temperature tables for R134A and look up 25 degrees Celsius.
Saturated R134A?
Yeah, saturated R134A.
There's no 25 degrees Celsius, there's 24 and 26.
Okay, but what's the pressure at those two?
646. Yeah. 685.
They're both a lot higher, or they're both lower than what we have, right? So what does that tell you about the state of the incoming refrigerant? It's subcooled, that's right. It's definitely liquid, it's subcooled. So what we would do is approximate the enthalpy coming in as HF at 25 degrees Celsius. This is what you would do if you're in 220, right? You would just look up 25 degrees Celsius, look up HF. And now we can improve on that because I gave you an equation that does that. You can actually modify it based on the pressure. Now, by the way, if you look up the saturation temperature, if you look up the saturation pressure and you actually interpolate it, the saturation pressure for 25 degrees, let's say at 25 degrees C, comes out to 666.01 kilopascals. Okay. And the conspiracy theories start flying, right?
What is that equation called?
This is just a better approximation for a subcooled liquid, that's all it is. It's kind of something that's not terribly important in class.
Same thing.
Now we're running out of time, so I'm not going to look it up. Just believe me that you can go to T1 and you can get V sub F, you can get H sub F, you can get P sat, right? You have to interpolate all of them. I've already got P sat, right? So we've got this. We know the actual pressure is 800 kilopascals. I'll leave it as an exercise for you to do to show that this enthalpy comes out to 86.52 kilojoules per kilogram, because all the HF and the VF have to be interpolated. Okay? But there's the enthalpy coming out. That means that the enthalpy at 2 is the enthalpy at 1 is 86.52 kilojoules per kilogram. Because it can't change. There's nothing to add or take away energy from that stream. Now, go to the line that's -20 degrees. And tell me, what is HF at state 2? So at -20 degrees, what is the enthalpy of saturated liquid?
25.49 kilojoules per kilogram.
Good. Somebody else? What about Hg?
238.
You notice something? The actual enthalpy of the exiting stream is between those two. What does that tell you about the exiting stream? It's mixed. It's mixed. You got some liquid and some vapor, so there's equality there. In fact, the quality in state 2 is H2 less HF2 divided by HFG2. Okay? I won't plug in all the numbers. I'll leave it to you to show that this is about 0.2867. So about 28.7% is in the vapor phase. Okay? It's easy to see. This goes right here. This goes right here. And to get this, this is just Hg2 less Hf2. Okay? So you can do all that at home if you want. So there's the quality at the exit. So what I'd like to do is come up with the internal energy at the exit, okay? Because I think that's what they asked for. So the internal energy at the exit would just be the internal energy of saturated liquid plus the quality. By the way, this would be state 2, UFG from state 2. So we're going to look up internal energy instead of enthalpy at the exit. Okay? When you do that, it's 25.39 kilojoules per kilogram plus 0.2867 for the quality, multiplied by 193.45 kilojoules per kilogram. I'm out of space and out of time. That comes out to about 80.85 kilojoules per kilogram, which is what they asked for. There's the enthalpy in the exit stream. I'm sorry, internal energy.
That quality equation, where you have X2
Mhm.
equals H2 minus, we've already seen that.
We have seen that many times. In fact, I had you write down a generic equation that says X equals Y average less Y of liquid divided by Y of gas less Y of liquid, which we usually call YFG. Plug anything in there you want. Enthalpy, entropy, internal energy, will all come out the same. Specific volume.
The very first part, I lost you a little bit on there.
All right.
So P1, 800 kilopascals.
So what's this? This is the saturation pressure that goes with 25 degrees. So if you look up 25 degrees,
But it's not on there.
you'll have to interpolate, but you can see this is between them. All you do is add those two divided by 2. It's right.
So what do we need to say?
Why do we need it right here? Because this is a measure of how far the pressure is from saturation, which helps us determine how far H1 is from H2.